molar mass is the mass of a mole. It is exactly what it says it is. And so the molar mass, or the mass of a mole, is going to be pretty large. If a mole is a huge number of these tiny things, the mass of that quantity of these tiny things is going to be a significant mass. And so that's measured in grams. Right? A laboratory size scale for a laboratory size amount of these tiny, tiny, tiny particles. So if I want to get the molar mass for something, if I know what that something is and what elements make it up, I just need to look at the mass on the periodic table. So the mass on the periodic table, as we said, is the mass of an individual thing in AMUs, or it's the mass of a huge number of these individual things in grams, which is nice. The periodic table gives us two relationships. The relationship between grams and moles, and also the relationship between atoms and AMUs. If I have a compound, then I just add up the individual masses of each element involved in that compound, and I have now the mass per mole of that compound. So if I have a mole of water, it's going to be 18.02 grams. So if I go on the balance and I measure out 18.02 grams of water, that's Avogadro's number of water molecules. That's a very huge number of individual particles. Right? So I have now a relationship between when I measure something out in the lab, now I can determine how many particles are actually there. That's really useful, especially when we start setting up chemical reactions later in this semester. You'll want to have two substances that you're going to put in the same container and they're going to collide. You want to set it up so that if one molecule of substance A collides with one molecule of substance B, you want them to be present in equal numbers. So you can have equal numbers of collisions and everything can have an opportunity to react and undergo this change. So you need to be able to use the molar masses to say, well, I actually can calculate how many molecules of molecule A I have and make sure that I put in an equal number of individual molecules of molecule B so that they're colliding and have the opportunity to react fully. So molar mass is really useful. You just want to make sure you're aware. If you're dealing with elements, sometimes the elements come in different forms. So we talked about this when we talked about molecules. Oxygen comes as O2, or it can come as individual atoms, which are not as likely because it's a little bit unstable. Or it could come as O3. So we know that's another way that molecule atoms can share electrons to make their noble gas configurations complete. So if you just say, I have a mole of oxygen, what does that really mean? How many atoms are in a mole of oxygen? Well, it depends on whether I have a mole of oxygen atoms, or whether I have a mole of oxygen molecules, or whether I have a mole of ozone molecules. Right? So if I have 1 mole of oxygen atoms, that's 6.022 times 10 to the 23rd atoms. If I have 1 mole of oxygen molecules, that's 6.022 times 10 to the 23rd molecules. Right? So, as we said, Avogadro's number doesn't carry a specific identity of the items that we're counting. It's just a number of items. So I could have that number of oxygen atoms, or I could have that number of oxygen molecules, which have the formula O2. So if I have a mole of oxygen molecules, how many atoms do I have? 2 moles, right? Because each molecule has 2 atoms. So if I multiply Avogadro's number by 2, that would be how many individual atoms of oxygen are present, right? So just make sure that you're aware of exactly, if you have a mole of something, what is that something? Because the formula of the thing that you have a mole of will tell you how many individual atoms are in that, and then you can determine how many moles of each individual atom you have if you need to know that. Here's another example. So here we want to take advantage of the periodic table to use it to give us some grams per mole relationship. So if I want to know how many moles of carbon there are in 25 grams of carbon, this is a very practical type of question. If I measure out 25.00 grams of carbon, I want to know how many individual molecules, not molecules, individual atoms of carbon I have, or how many particles or a number that represents the quantity of individual atoms, that's a mole. So the periodic table mass for carbon is a relationship. It's the number of grams equal to a mole of carbon. So I can use that as a relationship. 12.01 grams of carbon in 1 mole of carbon. Right? So when you have a unit per another unit, that means that quantity in grams is equal to per 1 mole or equal to 1 mole of that substance. So I would just divide 25 by 12, the grams cancel, and that would tell me the number of moles of carbon I have in that sample. And I can do that for any substance, whether it's an element or whether it's a compound. If I add the masses on the periodic table for the elements involved in the compound, that gives me a relationship between grams and moles. So if I want to know the number of moles, if I've measured out a certain number of grams, this is how I would set up that conversion. One step using that relationship from the periodic table. So this just gives you an idea of what formulas to use and how to set up your conversions. If you want to use this, it's on the formula sheet. You're welcome to. But really, you don't need to memorize what relationship you need to get from grams to moles. You just need to think about what unit you have and what unit you want, and what is the relationship between those units. Set up the relationships and then use them to convert the units. And that just basically requires that you do a lot of practice so that you can get used to using it. So the molar mass is the relationship between grams and moles. It's for atoms and it's also for compounds. So if I'm dealing with CO2, I want to know how many moles of CO2 do I have if I have 10 grams of CO2. Well, I would start with the given information. And I would say I want that information to be converted to moles, so I need the relationship between grams of that and moles of that. The relationship between grams and moles comes from the periodic table, if I know the identity of the substance. So I'll take the mass of 1 carbon, 12.01, and I would add that to the mass of oxygen multiplied by 2, which is 16 times 2. Add that all together, I get 44.01. Right, so that's the number of grams of CO2 equal to 1 mole of CO2. Then I just divide. 10 divided by 44.01 will give me my answer in moles of CO2. So I can do that for molecules and compounds as well as individual atoms. Questions about that? What is the what is the smallest possible molar mass? Yeah, 1. That'd be the smallest. I mean, hydrogen has 1.008. That's on average for hydrogen. Its average molar mass. If I had a totally pure sample of hydrogen that only had hydrogen with the isotope with a mass of 1, then it would just be 1 gram per mole. But I can't have less than that because I don't have atoms with less than 1 proton present. So if your quiz answer, when you calculated the molar mass in the quiz, and you got a number that was less than 1, you know it's wrong. It can't be right. That cannot be correct. So you know that something went wrong, and that's kind of a way to check your work. If you have the elements on the periodic table, you add their molar masses together to get the molar mass of the compound. But if, like on the quiz question, you're dealing with a substance and you don't know what the identity of the substance is, you don't have its formula, you don't know what elements are involved, and you're trying to calculate a molar mass, it's got to be greater than 1, or 1 at the least. So you can check your work that way and at least make sure that the answer is somewhat reasonable. All right, so here's another example where we can use some of these relationships. So here I want to know the number of individual molecules in the number of individual molecules and the number of individual atoms in 3.26 grams of water. So this, I already have a clue that when I'm dealing with individual tiny things, and I want to relate that to laboratory scale things, I'm going to need to use Avogadro's number as a relationship. So I can already establish that as a relationship between the number of molecules and a mole of those molecules. I'm going to need to use Avogadro's number if I'm trying to work where some given information is a large scale, laboratory scale, and some information maybe that's given or that I'm looking for is a super tiny scale. So Avogadro's number gives me the relationship between individual particles and moles. But I still need a relationship that involves grams, because if I'm looking for the number of molecules of water in 3.26 grams of water, I need some relationship that involves grams. So what should I use? I need the molar mass, right? So I need the mass of 2 hydrogens and 1 oxygen. And if I add that together, I get 18.0. I can use more sig figs if I want. I probably don't want that to limit the sig figs of my final answer. So since I'm limited to 3 anyway by this 3.26, I don't really need more than 3 in my molar mass. But that's going to be the relationship between grams of water and moles of water. Like the masses on the periodic table are always the number of grams equal to 1 mole of a substance. So now I've got the relationships I need. So I can use that to cancel the grams and convert to moles. And then I can use Avogadro's number to relate the number of moles to the number of individual molecules so I can cancel all this, and that will give me 3.26 divided by 18 times 6.022 times 10 to the 23rd gives me 1.09 times 10 to the 23rd molecules of water. So that's the first part. Any questions about that? So then, how do I figure out the number of atoms of hydrogen present and the number of atoms of oxygen present? There I can use the formula. The formula for a substance gives me relationships. It tells me for every 1 molecule, I've got 2 hydrogens. And for every 1 molecule, I have 1 oxygen. That's a relationship. 1 molecule of water gives me or is equal to 2 hydrogen atoms, which is equal to 1 oxygen atom in this particular substance with this specific formula. So if I want to know how many hydrogen atoms I have in this number of molecules that I've determined I have, oops, oh, that's fine. Then I just use that relationship, 2 atoms of hydrogen in every 1 molecule. So now the molecules cancel, and I would have my answer when I multiply that by 2. And then for the oxygen, I would set it up the same way. Except in the case of the oxygen, every 1 molecule has 1 oxygen atom. So when I cancel the molecules, now my units are atoms of oxygen. And so there's a lot of relationships here. Avogadro's number is a relationship. The molar mass is a relationship. The formula for a substance gives me a relationship between the number of atoms present per 1 unit of that substance. There's lots of different ways that questions could be asked that involve these relationships. So you really need a lot of practice with a lot of variety of questions to be sure that you'll be able to approach and solve questions using these relationships really pretty much no matter how they're worded. You'll be prepared for the exam that way. So make sure you do lots of practice with these.